Alright everybody, welcome to the next video. What we have here today is actually a 2-for-1 special. We are going to be covering both sections 6.4 and 6.5 at the same time. Mostly because they are very similar to each other and their goals are the same. It's just a little bit of extra information presented, not prevented, at the same time. So, what we're going to be talking about here is how to prove triangles similar by something called AA, something called SSS, and something called SAS. Now I know when you're watching this, you are probably thinking to yourselves, we already did stuff like this. We already used SSS. We already used SAS. Well, we're going to be using them again, and they're going to be a little bit different when it comes to similarity. But they do, two of those at least have the same name. New one is angle-angle, AA, which we will talk about what exactly that means coming up. But first, a little bit of review. How did we prove that triangles were congruent? Well, this happened a little bit earlier in the year, but the way that we did it was we first said that to show that two triangles are congruent, we need to know that all of the angles and all of the sides are congruent. But that didn't last very long. We moved on, and we then said, well, we don't really need to show everything, but if we know that all the sides are the same in the triangles, then we can say that they are congruent. Or if we know that two sides and the angle that's between them is congruent, then we can say that the triangles are congruent. Or if we have two angles in a row and then a side, we know that the triangles are congruent, if those are congruent. And if we have two angles and the side between them, then we can say that two triangles are congruent. And if it's a right triangle, we have the hypotenuse leg theorem, saying that if we had the hypotenuse and the leg being congruent, then the triangles were congruent too. Well, we can do pretty similar things when it comes to similar triangles as well. So, first one we have here is angle-angle. And the way this reads is if two angles of one triangle are congruent to the corresponding angles of another triangle, then the two triangles are similar. Now you may be wondering why we can say this when we only know that two of the angles are congruent between the triangles. It becomes clear when we look at two things. First of all, in similar triangles, remember that when we have these, all angles, and I should specify and say corresponding angles, are congruent. That's one thing we know about similar triangles. Now, why do we only need two of them? Well, we already know that when we have two triangles, if we know that these two angles are the same, and these two are the same, since both triangles have to add up to 180 degrees, then we know by default that this last remaining angle will have to be the same between the two triangles. So that's why we only need two of the angles to be congruent. And once we have that, we have two triangles that are similar to each other. All right, next theorem. Side, side, side. It reads, if the corresponding sides of two triangles are, and we're not going to say congruent here, because in similar shapes, sides do not need to be the same size. But they do need to be able to form ratios that will be equal. So we describe these sides, as we learned about before in earlier sections, we describe these sides as proportional. So if the corresponding sides of two triangles are proportional, then the two triangles are similar. And you actually worked with this in a few of the problems that you probably saw earlier in the chapter, earlier in the material, where you had to show that two triangles were similar, and one way that you did that was you made ratios out of all the corresponding sides, and you showed that they ended up all equaling the same number. That's exactly what this would mean. You're looking for those sides to form ratios that are all equal. We describe that as proportional. Side angle side. If an angle of one triangle is congruent to an angle of a second triangle, and the lengths of the sides including these angles are proportional, then the triangles are similar. I underlined including because that's a vocab word that we talked about earlier when we were talking about congruency, but you might not remember what it means. Just as a reminder, if we have a triangle, let's say that we know that, okay, let's label these points too. We have A, B, C, and let's make a second one that's supposed to be similar. We'll call it D, E, F. So let's say we know that angle A is congruent to angle D. If we're told that AB over DE equals AC over DF, let me write that down. AB over DE equals AC over DF. If we're told that information, then we can say that these triangles are similar, because AB and DE and AC and DF are the two sides that are forming angles A and D. This allows us to say that the triangles are similar because these sides are forming the angle that we're talking about. If we were told only that A and D were congruent angles and that AB over DE equaled BC over EF, this would not by itself be enough to tell us that these are similar, because BC and EF are not included sides. They're not the sides that are including the angle. They're kind of not attached to the angle at all. So it has to be the two sides that are making the angle. All right, so what we're going to move into then is a few examples of how this works. So our goal here is to prove that these triangles are, in fact, congruent, or similar, not congruent. So, looking at this one, we can see that this angle here is the same between the two of them. It's a right angle. And we're given that angle C is 26 degrees and angle H is 64 degrees. If we look at the first triangle, if that's 26 degrees, and we know that we already have 90 degrees, to finish the 180 degrees in that triangle, angle E, we would do 180 minus 90 minus 26, would have to be 64 degrees. And by that same thought, that means angle K would also have to be 26 degrees there. Now, the reason we need to do that is because just looking at the problem from the surface, we can't tell whether or not those two angles are exactly the same, the ones that are missing. But now we see that we have, here's an angle that's congruent between the two. Here's an angle that's congruent between the two. That means that these two triangles are similar. If we wanted to make a similarity statement, we could say something as simple as CDE is congruent, or not congruent, sorry, is similar to KGH. And we would say by angle. I know that we found all three angles, but we didn't really need to. As long as you have two, you're good. It just so happened that we found all three in this one. If you do have two, all three will end up working. Next example. Of course, we have a return of parallel lines here. Remember from our earlier units that parallel lines usually mean that you're going to be able to prove that some angles are congruent here. So what we can do here is with these parallel lines, if you can see here that angle R right there and angle T are going to be congruent because they're alternate interior angles. We could do that again for S and U, but we could also see that angle SVR and angle TVU have to also be congruent because they're vertical angles. I could find the last one and show it's congruent, but I don't really need to because our theorem is angle-angle. I've already shown that two angles are congruent. So I can say at this point that SRV is similar to UTV. So that one wasn't too bad. This one. Okay. So, I'm going to look at this right now, and I'm going to say, well, there's not really any way for us to use side, side, side here because we don't have any good way to find that last side. These aren't right triangles, so we can't use Pythagorean theorem. We don't know any angle measures, so we can't use trig or inverse trig. So, but one thing that we can say is that ACB, the angle, is congruent to ECD because those are vertical angles. So what we're going to have to do beyond that then is we're going to have to test out some sides and see if we have sides that are proportional. Now, looking at the shapes of these, which you're going to want to use a little bit of judgment with, it looks to me like if we were to flip CED around, kind of flip it upside down, it would have the same orientation as triangle ABC. So it looks to me like the 30 side matches up with the 18, and the 9 matches up with the 15. So what we should do then is we should set up 30 over 18, and we want to find out what that is exactly. Well, if we reduce it, divide both numbers by 2, we get 15 over 6. If we reduce those by 3, we get 5 over 2, so that would be sorry everybody, messed up a little bit. This 18 would actually end up being a 9 down here when we divide by 2. Dividing this by 3, we get 5/3, and we'll just sort of leave it at that. Doing it with the other pair, we have 15 over 9. Well, we had 15 over 9 as a previous step in the last one, the one that we just did above, so that's going to turn into 5/3 as well. Notice that these ratios here are the same. So, what that means is that these two triangles are in fact similar because we have the two sides that are creating the angle that are proportional, and also we have an angle that is congruent. So, we can say that ABC is similar to DEC by, this time we're using side angle side. So, there you have it. This is how similarity works. This is, you know, a pretty big deal when it comes to showing that things are similar. Because now you don't have to show that all of the angles are congruent and that all of the sides are proportional. You can limit what you're doing a little bit. So, hopefully you found this video informative. Stay tuned. Another video coming up for 6.6.